It's the Fourier transform, the breakdown of the signal.
Yeah.
I see it.
I don't know, I guess I didn't think about that.
Okay, let's start and just run the code and see what happens, and then it will be long and boring story of what it is.
Which one should we run first? Should we run the C or the
D is bad. D is they differ just by one letter. So did you get to guess what you need to do? Yeah. But do it on your stations.
Oh, it's going. Mine's like almost in line with yours.
Oh, okay.
A little bit after.
So what did you observe?
Is it the box getting smaller?
No. Initially, just explain what you saw.
Like starting off as that like tall peak leading, and then it kind of like flattened out and spread out.
Does the center stays in the same place or moves?
Should, right.
Okay,
And then
that's it.
again.
So guess what is this peak? Total here. It was there is a popping up like 5 windows. So what do you think should I put on the Y, X and Y labels?
Probability.
It's like probably
Probability density. The probability is one number. Here is distribution. Right? So wave function squared. And X is X. Right? So what is yeah, the PDF has sign up list from previous year. I just downloaded it in case we need to see the list of subjects. It's mostly for me to what to follow, which subjects to explain. So, what is the how many dimensions are in this problem? Good. What is the potential? And for each point of problem, Hamiltonian consists of kinetic energy and potential. Potential energy is typically like curve. Right? Today in class we started quadratic. Before we did the square box. And before we did what?
I know.
You know, you do.
What is what? You just have like a line.
Yes. So free space.
Yeah.
So which of these three cases are shown here?
This looks like the free space.
Yes. So it's propagation of Gaussian wave packet in free space, right? So it is the stuff that we were suffering for several weeks, right? So the center moves and the shape expands, right? So it's basically a prediction of the future in a narrow sense. Everyone agrees. Okay. So which ways of predicting future do you know? How many?
Which what?
How many? Huh?
4. Do I know 4?
Okay. So which one of them is implemented here?
What was the question?
How many ways to predict future you are aware of? You're holding like private. Or gamer for computer games. It's still the class. Just guess. You probably. I'm not asking myself and you to list all of them because I have no doubt that you remember all of them.
Sure. Schrodinger.
Huh?
Schrodinger.
No.
Well, we have like time.
Huh?
About the different.
Well, you always have time if you predict the future. The future is always in forward in time.
So like location or position. Is that one thing we're trying to calculate, like determine?
Well, there is a evolution operator, discrete propagation, eigenstate expansion, and Heisenberg equation of motion.
Heisenberg.
It's not Heisenberg because Heisenberg tracks only one observer, or maybe two observables.
Eigenstate expansion.
Huh? No?
Oh man, it's gonna go. It's like when you're taking a test and you get some.
Multiple choice.
Yeah.
Whatever the last one I would choose would be.
So there are numbers 1, 2, 3, 4. Evolution, discrete, Schrodinger, Heisenberg. We already checked that the last two do not work.
Evolution.
Yes.
It says that on the code somewhere.
Good.
I just realized.
So if you see
Oh,
this,
it's time evolution.
if you see this little PDF in whatever a little less than 2 weeks, I hope you all will agree to cover these materials. And now it's before that it's more my job to tell what they are so that you feel comfortable and then become experts in narrower part and then teach it to others.
Yeah. Maybe I opened it twice. It's possible. It looks like I did.
I thought that was
Yeah, that makes sense. I'll just close everything. Try opening quick. Because I have two big things.
Okay, so teach me what is the evolution operator. Oh, it's too. I'm taking too short pages. This code is the rest of the semester. You'll be doing nothing rather than running this code with different conditions, and your research projects will be based on this code. So this code is our life. The class material will be just entertainment. So before utilizing it for your projects, we want you to master our skills in understanding, like, well, if I say each line will be too much, each second line of the code. And I'm going to cover the principles and like, it's not, it will be too much to cover, to absorb everything for a single person right now. But if you have an idea which of the subjects you are going to present, you can focus your listening abilities on that certain time and absorb it more efficiently and then present. So I would appreciate your help in defining evolution operator. What's that? Assuming that you were so attentive during the lectures and to remember everything that was there. I'm not asking for exact formula, just basically what it does.
They kind of like show how the particle or wave will act over time.
Okay, so if you start from certain distribution, it helps to get distribution the next time.
Yeah.
And it has the past, it has a multiplicative nature, right? By multiplying evolution operator on the wave function of the past, you get wave function of the future. Everyone agrees, right? So, what were we talking about at the very first week or 2 weeks about phase accumulation?
They kind of add on to each other. You mean?
Yeah. It's kind of like multiple waves will like add together. Is that kind of?
That's kind of what I was thinking, but
So, if particle is moving, it accumulates the action along the trajectory, linearly or by some law. And then this action goes into a oscillating exponential, and it is what makes the wave. Right? More or less? So the evolution operator is related to this accumulation of phase. Now, what is action? Action should be minimized because we do not want to act, right? So it's integral of energies over time, right? And it is our common agreement to have minus I over h bar generally integral of Hamiltonian over time from past to the time of future. And if our future minus past is very short, then we replace this integral to just multiplication. Minus I h bar h times delta t. Make sense? At least no one objects.
What is big T again?
Kinetic energy.
What? Kinetic?
Kinetic, U, potential. So, if you want to start from scratch and abandon the code that you got in the email and just write the code yourself, and you believe that this is a correct formula for predicting future, what would bring you a confuse? What is not? What needs additional work out in here?
would the imaginary value cause any issues, or that is fine?
So the wave function depends on both position and time, right?
Not position.
And position, since we are in programming world, they are discretized, right? So it is a vector. And it is not a problem. It doesn't create any issues. So our psi is if our, let's do it this way. Our x is represented by set of discrete values. x1, x2, x3, x4, n times, right? And they are all offset by small values. And then our wave function at each specific time will be like wave function at point 1, wave function at point 2, wave function at point 3, wave function at point n, right? This is not a problem. But how do we act, how we program multiplication of this exponential with Hamiltonian time onto such wave function? How this exponential should look like? What should be the structure of this operator?
You mean other than specifically affected?
Okay, vector. John suggests something about vector, and Alyssa wanted to say also something. Okay.
I was just gonna say it should probably be squared, so it can be multiplied by both of those.
Square, something square. I like it very much. Something square. What else? We are approaching truth. It's not nothing wrong. We're just what? Yes.
I actually have a different question. What is U again?
Evolution operator. I do not deserve highest grade myself because I have ambiguous definitions. U here, let's put letter V, potential energy, and U here is evolution operator.
And that's the same as the one up top.
Yes. Thank you. But how? What were you doing on Monday? I know your schedules are very busy and you were doing 1,000 things, but I'm more selfish. What were you doing in PChem class on the lecture? What was the subject? It looks like you're scrolling your memory like a booklet. Let's go to another page.
Equation of motion on it?
Yes. Equation of motion for what?
Expansion coefficients, that's what I have written.
Okay. And expansion coefficients are representation of wave function, right? So it was Schrödinger equation in?
Matrix form.
Yes. And here I was asking how to represent this evolution operator so that it can be multiplied with a vector. What we can multiply with a vector? Of course, we can multiply another vector, but what else can be multiplied by from left onto the vector? So the idea of Monday meeting that any operator, any differential operator, can be represented as a matrix. Right?
Did you say that one more time?
Any operator can be represented as a matrix. Good. Evolution operator is operator. I'm very logical. Therefore, evolution operator can be also represented as super. So we need to find a matrix that would represent evolution operator. And I set up a little task for me to guide you through background ideas, how to define the matrix that will represent evolution operator. It will be only the task for the brave person who will select the first couple of subjects, but it is a fundamental background for all of us. So I will go a little slower on this subject, and then as we go for the rest, I'll go quicker. So if you're already getting bored, I will show part of the code that corresponds to this evolution operator matrix, but probably it will tell you nothing because I will jump forward 10 steps. You enjoy the line of the code, but then we will go back with slow logic. Focus on the screen. Come on, yes. A little more. Out and up and down. Is the font visible here? Okay. Okay, so line 118 is the, you see here, alternative definition of evolution operator. And by looking onto what you had on a blackboard, you recognize exponential in matrix form, imaginary unit, tau, you can guess that it will be time increment, h bar, you can guess it is a Planck constant, and CHEM is not a food. It's an abbreviation for Hamiltonian, right? And you can guess that by applying this g tau 2 to wave function, one will get propagation in time for as long time duration as defined by variable tau. Okay? So as soon as you possess some CHEM, you can do g tau evolution operator, right? And in this aspect, in the equation here, we do need we already recognize that evolution operator that we call g tau 2, it depends on another matrix. So Hamiltonian should be also matrix, right? Which is also not a big surprise. And now we need to find how to define Hamiltonian as a matrix in a basis of discrete space. Okay, and Hamiltonian is summation of kinetic plus potential, which means simple logic. Evolution operator is matrix. Hamiltonian operator is also matrix. Then matrix is composed of, then the components of the Hamiltonian should be also matrices. Both kinetic and potential energy should be matrices. I'm telling you right away that if we are dealing with free space, as Morgan has noticed, then potential will be equal 0, so we don't care about potential right now. So we need to find a matrix for kinetic energy operator. Make sense?
So the potential is 0 because we're in free space.
Yes, well, it will be matrix of the like n by n, same size as our discretization on X, but it will be filled with zeros. In this particular case. Later on we will be doing something more advanced to it. But right now we are going to repeat the pathway we did in theory, in class. We did free space, box, and then we started harmonic oscillator. Let's start with simple thing first.
We're starting with free space again, and then we'll...
Yes. So free space. So we need a matrix that will represent kinetic energy. You don't object the logic yet. Okay. If we need a matrix that represents kinetic energy, and we remember that kinetic energy is p squared over 2m. What's the next logical step? Find which matrix will, or p squared is p times p. pp over 2m. So we need to find matrix for momentum operator. And momentum operator, how do we define it? Minus I times h bar times d dx.
Is that negative I over h bar?
Negative I, to my memory, it's multiplied by h bar, but I am a hero of mistakes. If you find, I wouldn't be surprised if you, please point them for an extra credit. So we are narrowing down our task. We do need a matrix that would correspond to derivative over space, over coordinate. Okay? So matrix form of derivative operator. Matrix of derivative. And as soon as, well, you can cover your face and start laughing like, why do we need it if the code is already available? We're not going to write it over, right? But suppose that you are planning to write the code over. Then through the steps that we just discussed, we can, as soon as we answer into this question, which matrix represents derivative operator, we can immediately roll logic in the backwards direction. Form kinetic energy operator, form Hamiltonian, put it into exponential, and then apply evolution operator to propagate wave function. Okay? Whew. Do not hesitate to stop me. If even if you just lost track, tell like it's boring. Tell something more funny.
So the G-tau2, that doesn't have any significance other than just that's what the evolution operator is called in the code?
Yes.
Okay.
And it is like a heart of the code. The this code is our life for the rest of semester, and the G-tau2 operator is the life of the code. What is derivative?
It's the slope.
Derivative slope. Okay. You got A in philosophy. But if you want to quantify it a little bit more, and with philosophical mindset, like, it's not a correct question. Derivative of what in respect to what? But derivative of wave function in respect to position. What's the definition?
That being
I'm just interpreting that you all are hesitating to spell out childish, simple things because it's so simple and you all know. So
I was going to say velocity, but I'm not sure.
velocity, but if I do have values of function at each position, at x, x plus delta x, x plus 2 delta x. Right? So with this discrete information, how would I define derivative? You know it. You wouldn't survive until this level if you wouldn't pass calculus. And the definition of derivative is like lecture 1 of calculus in any school.
Oh, it's the length of the line.
It's more length of the line is more complicated. Derivative is much simpler. When you talk velocity, it is not wrong.
Rate of change?
Oh, perfect. Derivative are slow.
That's right.
It's also rate of change. Rate of change. So you all are getting A in philosophy and in linguistics. But now let's quantify it. Let's generate an equation for derivative. Like, if I do have these values, can I compose something of them that would give it a derivative? D psi over x equals to I'm sure you know. So slope, rate of change. So if you have your x and you have your psi, slope is a tangential line, right? So it is the rate of this one to this one, right? Rate or slope. Okay, next step. Do we, if this information is provided, do we have delta x here? We do, we can use it. Do we have delta psi? How can we define it?
You do n delta x, starting with n equals 0. And then you'd have psi of x plus n delta x. When n equals 0, just be 0. Or of x plus n delta x.
X plus n delta x and
And going from, I guess, 0 to infinity, but because at least that would be a way to represent it. And that would be over x plus n delta x without psi.
x plus delta x. What you're telling me is not wrong. I just so if this is x and this is x plus delta x, this will be psi of x, and this will be psi of x plus delta x. Right? So how do we define delta psi?
That's the x plus delta x.
Well, x plus delta x serves as an argument of what?
Psi.
Okay. Should we put minus? We subtract this much minus this much.
And then we just subtract psi of x.
Yes, perfect. Morgan performs outstanding. Divided by delta x, right? So this is engraved in stone as the fundamental of calculus, right? Whew. Do you see any, does it look like a matrix? Not right now. I wouldn't see any connection. But we do have an order. We have a, if we would serve as scientists for hire, our work order is to represent derivative as a matrix. So where is the matrix? It's, we are going over the most creative thing of the most important operator of the most important code for this class. The rest we rolling through naturally and easily. So which matrix will represent this stuff?
Would it be a matrix of
which coefficients? I'm not arguing. Maybe it's some coefficients.
Is the matrix coordinate?
Yes.
Well, I guess if we have to plug it in, we have to be.
Why do you use the matrix of the evolution operator?
No. First, we construct matrix for derivative, then we plug it into momentum, then we plug it into momentum squared, then we plug it into kinetic energy, then we plug it to Hamiltonian, then we plug it into evolution derivative. But it's all it all will be instantaneous as soon as we define the momentum or derivative of derivative. So it is the only problem that we actually need to solve.
Be like a matrix of like delta psi.
Mm-hmm. In nominator or denominator.
No, denominator.
Or?
Denominator.
Yes. So let me delta psi in the nominator, I agree, and delta x in the denominator. But everything is correct, but let me add some details, and then I will ask your intellectual help once again. So this one is definition of derivative for the point x. Okay? And if I want to be very symmetric, I don't want to be symmetric. I want the equations to be symmetric. I can set up here psi of x minus delta x, and here point x minus delta x. And here we have a limit of delta x goes to 0. Limit delta x goes to 0, right? It is what you enjoyed in calculus. Now, no one will criticize me, I hope, if I rewrite this definition as psi of x plus delta x minus psi of x minus delta x divided by 2 delta x. In the limit of 2 delta x goes to 0, right? So I still compare two nearby points as soon as they approach to each other. If you do not like it, please criticize it. Or if you don't care. So it is our derivative in point derivative prime, derivative in point x. I'm going to mute the screen and write something in the middle because it will be a simple idea, but it will need space. Video mute. Okay.
What's below the limit on the last thing you wrote there?
2 delta x.
Equals goes to 0.
Yes. So, I hope you are sufficiently intrigued and you are not yet tired. I'm going to repeat this definition several times, intentionally. So I will rewrite it. So psi of x, psi prime x, derivative, equals psi of x plus delta x minus psi of x minus delta x divided by 2 delta x. From the definition, you know that if the curve is not straight, if curve has a curvature, the derivative will be different in different points of space, right? Therefore, it is very reasonable for me to define psi prime of x minus delta x. And then I will tell it as psi of x minus 2 delta x minus psi of x, right? Should I explain or it is clear? So I just shift this definition by 1 delta x backwards. So I subtract 1 delta x from here and 1 delta x from there. Right? If I want to define derivative in point x plus delta x, I will shift definition forward. Psi of x plus 2 delta x minus psi of x.
The top one, those two would be switched around, wouldn't they?
Yeah, they'd be
Yes.
they'd be reversed.
Yes. Thank you. Thanks much. And if I want to practice it, I can repeat which way. Plus 2 delta x minus 2 delta x, and I can do many of those. But probably these 3 examples will give us a pattern. So we subtract neighbors of the function in a symmetric way, and in the denominator we always have the same 2 delta x, right? Do you see a matrix in this notation? No? I do see, and I'm going to write the answer, but fairly, I do not have any pedagogical steps to make a connection for next step. I will declare and then we'll work on it and analyze together. So, assume that I do have a vector that consists of psi of x, psi of x minus delta x, psi of x plus delta x. And it goes further, psi of x plus 2 delta x. Ding, ding, ding. Psi of x minus 2 delta x. Okay, I can do it. Now, here I do have an unknown matrix that is unknown for next 5 minutes, and then it will be known. And I want to find elements of this matrix in such a way that after practicing multiplication of this row by column rule, I will obtain psi prime of x, psi prime of x minus delta x, psi prime of x plus delta x, and so forth.
So that first matrix will equal the product of the second two.
This vector,
Oh, that vector.
first vector, will be equal to product of this unknown matrix by this vector. So as an input, we have this blue vector of the function. As an output, we have a vector of derivatives. Okay? So right now we are looking not the whole matrix, but segments of like 5 by 5. Now let me formulate a very minor, simple question. With which coefficient psi of x minus 2 delta x contributes to derivative in point x? And I will answer myself to show you the pattern. 0. Now, with which coefficient, with the function of x minus delta x will contribute to derivative in point x?
-1.
Correct. -1 divided by 2 delta x. Right?
Wait, why?
Because of this. So psi of x minus delta x divided by 2 delta x contributes to the derivative. And if you multiply row by column, this row by this column, we are going to reproduce this definition. Let's continue the pattern and then return to it.
Is that -1 over?
-1 over 2 delta x. So according to this definition, with which coefficient the psi of x enters to psi prime of x? 0. With which coefficient psi of x plus delta x enters into this psi prime of x?
2 delta x.
Plus 1 over 2 delta x. With which coefficient psi of x plus 2 delta x enters into this definition?
0.
Uh-huh. Okay, now let's go to this one. Psi prime of x minus delta x. With which coefficient the psi of x minus 2 delta x enters this stuff?
-1 over 2 delta x.
Yes. 2
Maybe
delta x.
the row below you shift the 1 to the left a little bit.
Mm-hmm. The psi of x minus delta x, 0. Psi of x,
1
1 over.
yes.
0, 0, 0. 0, -1, 0. 0.
Okay. So you all together as a class did a great discovery. You found how to represent derivative operator with a matrix. You're not comfortable with it? Or it is just too
No, the
unusual?
chart makes sense, but I just, for the top row, because it doesn't
Well,
go around,
if it is infinite column of these values, it will be infinite matrix.
Okay.
And there will be specific tricks how to treat first and last row if the matrix is finite. I'll tell about it a little later.
Okay.
So, which trends do you observe? What will be the values on the main diagonal when, if you call this like number n plus 1, n minus 1, this will be again n minus 1, n plus 1, n plus 2, n minus 2, n minus 2, n minus 2. So when, maybe not n, but a different index. K and n. If the indices coincide. Yes?
Is that one at the top right seems to be +2?
Yes, thank you. I told you. I'm a genius of errors. So, which values do you have on the main diagonal when elements are equal to each other? 0. What do we have on the main subdiagonal?
The -1.
Yeah, and first upper subdiagonal. Yes. Whew. Basically, we are done. I will reformulate it and maybe write it in more concise form, but it is. It was the center of the course and of the lab and of the rest of whatever we will be doing.
Now, does that, like, if you were to have a bigger matrix, do those end up repeating somewhere else eventually? Okay.
So no one will criticize me for putting 1 over 2 delta x out of brackets. And then it will be just minus 1 minus 1 minus 1 plus 1 plus 1 plus 1 plus 1. So such matrix is a matrix of derivative. Good? And if you plug in this matrix into if you multiply it by imaginary unit and h bar, it will be matrix for momentum operator. If you take square of this matrix and divide by mass, it will be kinetic energy, which is equivalent to Hamiltonian for free space. And then you just plug it into exponential and call it evolution operator, right? So quite simple. So now I am going to, oh, it's too early for me to relax, but we need to go over like lines of the code. But you may want to make notes yourself what you noticed. There will be nothing more complicated than what you already covered. And if you make notes by your own words, it will be maybe better than what I was trying to say.
For writing in code, is it possible to make comments in different code?
If you put percent, anything after percent will not affect how code is running. If you change the name of the code and resave it under different name, you will not affect the older code. So you are very welcome to modify it, and you are more than welcome. You will be inquired to make modifications to the code. Your projects will be dealing with making modifications. Whew. I'm ready to stop and relax, but we do not have too much time. So I wanted to say a little bit more so that we fit all interest stuff in 2 weeks, and then we'll go over. So in atomic units, Planck constant and mass are 1. This variable number of points is how many discrete spaces. So delta x plus 2 delta x plus 2 delta x plus 3 delta x, total endpoints in this code will be 200. But later on we could change and the variable dx will be offset between 2 points. If you type dx, it will show 0.4. The units in atomic units, the atomic unit of length is Bohr radius, is distance between proton and electron in hydrogen atom, and our dx is about half of this, so like quarter of an angstrom. So it's but if you will be willing to make finer grids, you can modify this variable. Tau is time step. Skip that.
Is that like seconds?
No, atomic units of time. And why one atomic unit of time is like no, its fraction is like about 1/40 of a femtosecond. So if you need 1 femtosecond, you need 40 atomic units of time. I'll try to remember and tell a little more about units in the class. What else? X is just grid points. So if figure so we have 200 points, and offset between points is about half, so our space goes from 0 to 100 in atomic units. So here in this code, the variable v is used for potential, and I multiply whatever was defined by 0 just to remove it, but later on we will play with potential. And then there is okay, I know what to say. The variable tau is set as fraction of atomic unit of time, and it is a small fraction of femtosecond. So it's really short interval of time. Predictions over the interval of fraction of a femtosecond is not a big scientific achievement. We need to predict behavior of system for longer time intervals. If I do have a procedure that goes from time t to times t plus delta t, can I go to time t plus 2 delta t? Right? How do I do it? More, yes, increase delta t in it's line 118, I think. This work. 118. Yes. So we can just put tau multiplied by 2, or multiplied by 3, or multiplied by 10. You're absolutely correct. There is nothing wrong with this. But there is a practical observation that doing this evolution operator with longer time intervals accumulate numerical error. But let me. Is it okay if I remove these writings? And if needed, I hope they will be recorded anyway. So you already got the logic. Matrix of derivative, momentum, kinetic energy, Hamiltonian evolution operator. And I'm going to write absolutely the same thing. So if you have psi of t, we apply this evolution operator, minus I h bar h delta t, we will get psi of t plus delta t, right? And according to Morgan, if I put here e to the power minus I h bar h times 2 delta t, psi t, the result should be psi t plus 2 delta t. Correct? I am not making my own fantasies. I'm just obediently follow what you suggested. But can we assume that here, so it was h times delta t plus h times delta t. Is it okay? Right? So if we have this like a and this like b, can we e to the power a plus b represent as e to the power a times e to the power b? Okay? So I am following what Morgan has suggested, but I'm doing it a little different way. E to the power minus I over h bar h delta t, e to the power minus I h bar h delta t. Psi t will give psi of t plus 2 delta t. So I didn't violate your instructions. Do you have any observations? I'm not showing it on the screen, and Chris will be watching it later. I hope it will not break through. I'm not so over it yet. So, any observations? No
Just 2 times.
yes. So previous knowledge are not required. Just try to make connections between objects that are shown displayed on the board right now. Do you see similarity?
I think it's the same.
Yes. So, how can I rewrite the last equation? Psi of t plus 2 delta t.
Do that exponential times the psi t plus delta t.
Super. T plus delta t. So, no matter where we are, if we need to move forward by 1 delta t, we just multiply current version of the wave function by evolution operator.
By the last one then.
Yes. If I need 3 delta t, I will just multiply first one by 3 times by the same evolution operator. If I need 4, I will multiply 4 times. So based on our programming skills, which command, so it's question to Steven, which command do we implement if we need to repeat the same operation several times? Yes. So let's scroll through the code and find the loop that does this thing. Let's compete if you can do it quicker than I. Find the keyword loop if it is available there.
Like around like 40.
Which line do you suggest?
Like a 4 and then end, like 45 to 48.
Okay, I'm going to focus first and then go to this line.
Oh, I see it. I see.
So 40. Well, there is for and end, but there is nothing about time, right?
Yeah, I'm thinking 170 now.
Okay, let's go see what you found in 170. Yes, for loop equals to 1 to n tau. And then what would be your interpretation of the variable n tau? If tau is in time increment, time interval, then n tau logically will be number of time intervals. So we will, if tau times n tau will be the whole interval for which we do evolution.
Does that be the amount of time? that
Yes,
passes?
yes. And if we scroll through this thing, yes, this is second most important line in the whole code. So wave function is equal to itself multiplied by evolution operator. So it is implementation of the stuff. So by going one step forward in time, we multiply it by evolution operator, which is our g tau 2, and then next instant we redefine. We tell like t equals t plus delta t, psi of t equals psi of t plus delta t. Just because we do not want to save too much information, to be careful about resources. Whew. Let's look on the list of the subjects. We may not, we could be not very far in the formal list, but we did most important parts, the key of the code. So we did principle of wave packet propagation, momentum operator, Hamiltonian evolution operator. Right? Let me put some signs that it is done. Okay. Done. These two are interesting and fundamentally important, but let's maybe postpone it for the next time. It's too much of abstract things. Let's do something more practical. I don't know how about you, but I feel like squeezed lemon after this subject. So the next, most important thing is evolution operator, and second important thing is principles of wave packet propagation, like that we just covered with the loop. Next thing I suggest we focus will be the initial condition. When you were running the code, you noticed that at initial time it is a Gaussian shape. Where in which line of the code the initial wave function is defined. So let's, if I would be writing this code from scratch, psi at time 0 could be called as psi naught. So let's scroll through and find the variable psi naught.
71.
Ah, you are so strong. You're quicker than I can imagine. 70, 71. Yes. So, very long line. How are we going to interpret this line? And I will erase something on this part of the board and right there. Not so much. Back. Forward. John can wave hand to be recorded. Yeah. So initial condition. let's read what is written here. So I'm going just to write down literally what I see in the equation. So psi naught equals square root of delta x exponential to the power I p naught x minus x divided by h bar. Another exponential e to the power negative x minus x naught square divided by what is next?
4x.
4xr. 4. I would call it sigma, but if I would recall it, huh?
Oh, okay. So
Like width
yeah,
parameter.
right.
But it's not the end of the story. Then the everything is divided by, I should put here a denominator and put 2 pi x bar and then power 1/4, which means square root of square root. How much does it remind you the Gaussian wave packet from the class? Is it similar or different? Or is it similar in one aspect and different in another? And you should be quite familiar. We looked at German money with face of Gauss, right? You were doing some homeworks according to your grading, everyone from Texas. So you should recognize this e to the power x minus x naught squared, right? So it looks absolutely as it should be for Gaussian wave function. This square root of pi x bar, probably we would also admit it so that upon taking wave function square, it will be only one square root, and then one would reproduce literally the Gaussian wave function. So these two things should be more or less normal. What are new parts that you are feeling surprised? If you care. If you don't care, you don't care about anything.
Psi naught is new, isn't it? Psi. Like,
There's a sign up.
Well, it is psi naught as function of x, right? It's not a number. It's a like vector.
Yeah.
Defined for each value. So this x is how to maybe put vector here, is the set of discrete values. And this psi is also set of discrete values. Like column vector. This is normal. This doesn't surprise me. But if I would see it for the first time, I would ask, like, what is this term and what is this term? So these two originate from regular Gaussian distribution. What do you think about this term, about this second exponential? Does it remind you anything from your previous life?
Momentum operator? No, that's not
Well, momentum operator, it is without zero. This one is a number. just scrolling our memories back into the stuff that we covered in the class. Do you have any, does anything clicks, any pieces of memory? What is the eigenstate of momentum operator? And what is the name for this function? Like if, I think it was homework 3, we did like phi sub k e to the power I p a k x. And when we were just starting MATLAB, Alyssa was making an example of the spiral. You were calling something? So stuff that accumulate phase, imaginary oscillations, spiral with fixed rate. A state with certain momentum. I'm looking for a keyword. So John suggests ground. But there is more than one k. If k equals 0, maybe it will be ground.
So, would it be the opposite, or like excited? I feel like that's not very
Well,
good.
there are too many. Any of k not equals 0 will be excited. But if we do this type of wave in three-dimensional space, and the phase will accumulate in a plane and propagate with momentum. There is a wave.
Wait.
John was great. Just swap words.
Plane wave.
Yeah.
Oh.
So it is a plane wave. Super. Now we are connecting things. I know it is not the stuff that you were planning to do all your life, to connect pieces of information from PKM class, but it looks like we multiply Gaussian by plane wave. And plane wave is a state that moves forward with certain velocity. So now let's guess why this plane wave is inserted here.
So that first chunk is the plane wave.
This one is a plane wave.
And is that a positive I?
Yeah.
Okay.
At least it is was written here. I don't remember how sober I was when writing it, but it is what it is. So why the Gaussian portion is multiplied by plane wave?
Change form. Like
But you remember when we start, if you run the code at initial moment of time before you hit enter, it's Gaussian shape.
Is it like, would that be sort of at like time 0 where the plane wave hasn't like occurred yet? Is that,
There is no time here, but the wave is already there. So what are your opinions? Let's do an experiment. We're doing too much abstract things. Let's locate. So I'm going to formulate a task maybe for myself to experiment. Experiment. Answer the role of plane wave by changing P naught. So let's locate which line of the code defines the value of P naught and change its value to negative or to 0 and rerun the code. Make sense? So if this plane wave that depends on the value of P naught is important, then changing the value of P naught, if you put it 0, then it will disappear completely. If you put it negative, some effect will be like opposite.
Is it already at 0?
Huh?
Line
What?
6, doesn't it already say it's at 0?
Let's look.
My P naught says 0.425.
Yeah.
Well,
Are you on C?
yeah, I'm on C.
I'm on D.
Okay.
Yeah, D. If you're on C, it shows 0 for P naught.
And if you're on D, which line should I go?
6.
Line
6.
6.
Okay.
0.425 from line 6.
Okay. And if you are on C, then your potential is not 0. You have, if you are running C, you already have some like a little comp that represents several atoms. It's fun to watch, but we want to start with simpler things. So I would try to put negative here, save, and run again. Figure and run.
Okay.
What do you see?
Goes to the left now.
So what's the reason of P naught?
The direction.
So it's value of momentum, right? What do you expect if you put P naught equals 0?
It won't move at all. You'll just stay in the middle.
Super. Now let's do another experiment. Let's plot the function psi naught. Just type plot Do you like it? Does it look like the stuff that you were expecting to see? Does it look like Gaussian? So something, I do not see X, right? It looks like some symbol. If I want to be versatile, it's symbol of heart, or if I am hungry, it's symbol of peach. Or you can be creative. So wave function has both real and imaginary parts. So it could be reasonable to plot real of psi naught and maybe I can do simultaneous x real psi naught, comma x imaginary of psi naught. Does it look like Gaussian function? Yes and no.
The real one.
But it has this negative things. I'm going to do another experiment. I will triple the value of psi naught. I put like minus 1.5 or whatever. Save, rerun, and then repeat this experiment of plotting. Run. So it moves quicker, right? You already answered this. So this little plane wave is added to initial wave function to provide momentum at time 0. And you agree that changing the value of P naught will make it move quicker or slower. But let's redo this experiment of plotting real and imaginary part. What do you see? Does it look like Gaussian function now? No. But how would you define? Would it look like a product of Gaussian function times something that quickly oscillating? Okay? So the density of fringes of the wave function determine how quickly it will move. But in space, like everywhere away from the center region, it is 0. So it's multiplication. If you do an envelope, absolute value, then it should be Gaussian function. So what if I do, comma, x, comma, absolute value of psi naught. You see, absolute value is Gaussian. Because real and imaginary parts, I'm going to enlarge it. Real and imaginary parts, they are like sine and cosine according to Euler. And if you take sine square plus cosine square, it will give absolute value and provide this absolute envelope function. And the only envelope function, absolute value, is something that we can interpret. So in it will give probability distribution where electron is located. Mathematically, internal structure of wave function does include these fringes, and there is a meaning of these fringes. But wave function itself is not a stuff that is observed in experiment. Therefore, we hide it and do not show it. Make sense? So we did answer the. We did answer the reason of this plane wave component. And the last thing, this delta x. Did we have it in class? Did we have it? Do you see any reason for this? Any ideas why the square root of delta x is needed?
Change in position.
Yes, but why? Will the function look differently if you remove this factor? If you change the absolute value, but the fringes will be at the same place, right? So in which circumstances we may need this square root of delta x?
Imaginary?
What is the goal of the course? Predict future in abstract way, but in more narrow, if we connect to instruments and experiments. Predict outcome. Yes. Observables. Predict what comes out from the instrument. Right? And the stuff that we always do is bridge wave function operator, wave function conjugated. Right? So we, if we try to serve real world and experiment, we always need to do wave function conjugated times wave function. Or if we need expectation value, we are doing integral operator wave function integration. Right? But right now we do not have differential operations. We represent functions as a set of discrete values. Instead of integration, we will have just multiplication of psi of x minus delta x star psi star of x psi star x plus delta x, and more elements before and after, multiplied by column vector psi x minus delta x psi x psi x plus delta x, and more elements before and after. So it will be row by column for normalization for probability. So if you want to do this operation of multiplying two vectors instead of literal integration, then we are missing dx. And our answer will be different from what it should be by this factor. And if you suddenly change the value of dx, you immediately accumulate the error. Can we just multiply? Can we multiply this stuff by delta x in here? If you multiply this product of two vectors by delta x, it will be absolutely equivalent to integration. Make sense? But we do not want to design specific procedure of multiplying these wave functions onto dx for convolutions. We can attribute square root of delta x to this wave function and square root of delta x to this function. Just redefine them. And if delta x is square root of delta x is included into the wave functions, then multiplication of these vectors according to the rule of row by column will be absolutely equivalent to the protocol of normalization of finding expectation values. So if you suddenly need to quickly answer why this delta x is needed, you can say for normalization. Normalization. Make sense? Well. Whew. What else can we do? Huh? No, different direction. So we done initial conditions P naught, right? And X naught is initial position where it is located. So initial conditions are X naught and P naught. Initial wave function is chosen as Gaussian. So we're done with that. In some sense, we already did normalization of wave function in discrete representation. We can double check it quickly by. I feel that you are tired. Me too. I'm just trying to stuff maybe a few little things before we depart. So what if I do psi naught prime times psi naught? You see it? So the initial wave function is normalized, which is great. So basically we did this one. In some sense we did not quite. not quite, maybe halfway. Size of simulation cell versus time of simulation. Did you observe the wave function to the wave packet to go through the walls and coming back, and to reappear from the other side? Yes. So when we are modeling momentum operator and Hamiltonian and all other stuff, it is a question of always what to do if we have limited size of discrete steps. What do we do with borders? One way is to put infinite walls on the borders so that wave packet will smash into them and reflect. And another one is to pretend that by exiting on like rolls the space into a like donut. So by approaching one edge, it reappears the beginning of the other side. And it is added just by adding one number at the top and corners of the momentum operator. So it makes the reappearing on the other side. The trustability of this method is a little strange if stuff reappears. Therefore, one can, if you select product of momentum, initial momentum, and time of simulation smaller than the size of the box, then it will not reappear from other side, and our method is absolutely reliable. If we take too high momentum or too long time or too small box, then it will bring this effect, which is nothing wrong with it, but it is not desired in this aspect. And Alyssa may know the concept that is abbreviated as PBC. Periodic boundary conditions, which I always, so this reappearance of wave packet on the other side is needed if we simulate infinite crystals.
I really did quantum dots.
Then it is bad grade to me in poorly explained in computational chemistry. I'll try better this year. Okay. Done with this stuff. I think we did about a half, and I will better stay here and answer questions because you got a lot of new information, and stuffing more would prevent us from digesting it intellectual vomiting. So done for today. I'll stay here if anyone generates questions, but I think it is sufficient for today.
Good.